It's time to get to the truth about radiometric dating. And I know for me, as a young Earth creationist, this has been one of the topics that has been pretty difficult. I mean, does radiometric dating really show that the Earth is 4.5 billion years old? If so, then what I believe about the age of the Earth is false. Well, I've been learning some really interesting things about radioisotope dating, and I'm here with my friend Jack Vann Kean, who is going to share with us what he's learned about radiometric dating. So, do you want to tell us a little bit about yourself, Van?
Sure. I used to, at one point in my life, not believe in God. I was probably agnostic. And I came to a point that I chose to believe in Jesus and ask God into my life and changed my life. But all through my professional career, I was a petroleum engineer, worked for oil and gas companies. All through my professional career, I had sort of my faith on one side and this evolution, Big Bang, that I never really reconciled. And so when I retired, I was given the opportunity to spend the past few years just researching the two and trying to reconcile my faith with science. And radiometric dating came up. I had a I have a friend who's from another country, totally different culture, and he asked me, "Van, why is this important? Why should I care about this?" Well, the reason is that for a materialist, the cornerstone of materialism is billions of years because both evolution and the Big Bang depend upon it. For a someone with a biblical worldview, it's a matter of trusting what's in the Bible. And if there are billions of years, then can the account in Genesis be believed? And if the account in Genesis is not true, then what else is in the Bible is not true. So that's why I see it as a particularly important issue to spend a little bit of time discussing.
Well, I'm looking forward to hearing what you've discovered as you've been looking into this. So, do you want to go ahead with your presentation?
Let's go.
Okay.
All right. Rebekah, who spilled the milk? We have these vaguely familiar characters here. There's a cat in the background. There's a broom in the background. What do you think? Who spilled the milk?
From what I can see here, I don't know yet.
You need more information. Is that what you're saying?
Yep.
All right. Well, let's try going to some more information. We have this unusual looking character looking in the doorway. We have broken glass on the right. I see a dog. It looks like there's a baseball on the floor, a ball of yarn on the table. What do you think now?
Still don't know. There's a lot of possibilities.
That's exactly right. You remember Sherlock Holmes, don't you?
Yep.
A book, Study in Scarlet. Holmes mused on this very topic. He observed that when we see a result, how extraordinarily difficult it is to reason backwards through a chain of events to get to a cause. And that's exactly what these two pictures show here. For instance, on this picture, we don't know what's on the other side of the room that we can't see. We don't know where the room is. If it's by a baseball field, that might lead us to one conclusion. So there's no way to know because of the high degree of uncertainty. And as you might guess, that's going to be one of the general themes of the talk tonight is uncertainty. And so what I'm going to suggest to you is that the age of the Earth is unknowable using radiometric dating. And the way we'll approach this is I'll walk you through the lead-lead isochron methodology. That's the gold standard for dating the age of the Earth. Talk about it from the materialistic paradigm. I'll give you a divine creation premise and see how it works out within this methodology. And of course, what conversation would be complete without talking about zircon? And I want to suggest to you this binary mixing model, and then of course we'll finish up with the buffet of conformational bias.
Looking forward to it.
All right. So the challenge to historical science tries to explain where did we come from and how do we get here. In terms of dating the age of the Earth using radiometric dating, the way that I would like to frame it is what you see here on the screen. Time moves from left to right, and there's three boxes. The initial conditions, the transient conditions, which are between now and then, if you will, and then, of course, the current conditions, what we can see in that room, if you will. This is a quote by, I should introduce Claire Patterson. I'm going to be talking about him quite a bit tonight. He wrote this paper in 1956, a very clever, interesting, well thought out paper called The Age of Meteorites in the Earth. Some of his research that he did was looking into lead in the environment. You might remember that there used to be lead in gasoline. That's probably before your time. And of course, negative health effects of that. He had a role in researching that led to removing lead, trying to reduce lead in our environment. He said in this paper, it seems we should now admit that the age of the Earth is known as accurately and with about as much confidence as the concentration of aluminum is known in westerly Rhode Island granite. You see what he's saying?
Not really. What does he mean by that?
Here's what he's saying, that he can make a measurement in granite today,
Mm-hmm.
and with the same uncertainty, he can estimate the age of the Earth. So,
Okay.
of course, what he's saying is, I don't have any uncertainty in the age of the Earth.
I see.
Right.
By the way, just to let you know, it's not before my time. I do remember when you could go to the gas tank, go to the gas station, and you would choose regular or unleaded. So I'm a little older than you think.
Okay. All right. All right. Here we go. Look at this table here that's on the right side of the screen. That first column is meteorite, and I just listed this Alinda meteorite, which landed in Mexico in 1969. It's one of the most studied meteorites ever. The method that was used dating lead, which is exactly what we're going to be talking about. And of course, the ages all come out consistently over the years. Patterson, I've got his age listed there. He tested different meteorites, 4.55 billion years. And you can see as a function of time through the 70s, 80s, 2000s, the age has always come back the same. It's consistent. This method is considered the gold standard. The other radiometric dating techniques are calibrated to this. So a couple of questions that I will ask tonight and hopefully answer is, does radiometric dating result in a unique solution, a single answer? And then does radiometric dating disprove a divine creation premise? Before we get into radiometric dating I need to give you some context. It's going to start with this nucleosynthesis. There was a absolutely brilliant paper written in 1957. It's generally referred to as the B squared FH paper after the authors. And they proposed that elements come from the stars. And they had quite a bit of observational theoretical support. This is even in 1957. Very little revision has been done since this point in time. And they describe fusion. For instance, in the sun, it's thought that you take 4 hydrogen elements, atoms, you fuse them together and you get 4 helium atoms, a positron, and 2 neutrinos, and a gamma ray in energy. And then in different types of stars, and when a star explodes, they posit that that's where the heavier elements come from. And I just put the equation up here of how it's believed helium is fused into carbon. Radiometric dating doesn't date the time since the element was created. It dates the time since it crystallized. And we'll talk a little bit more about that.
Okay.
The next slide, again, more context. The solar nebula. Now you've heard of this, right? And I'm sure you've studied this, of how did the bodies in the solar system form? Gravity-driven nebula of plasma, rotating disk, protostar, planetesimals, nuclear fission we just talked about. Asteroids remain from the planet-forming material, and meteoroids are asteroids that strike the Earth. So that's why I'm going to be talking about meteoroids, is it's thought that meteoroids, which are asteroids, date to the same time that the Earth was formed. So if we date a meteoroid, we're dating the Earth. And we could probably have another talk on this. There's a number of issues with the nebular hypothesis, primarily the angular momentum, which is probably something that, with the understanding of physics that we have, makes this conjecture a little bit hard to support. Okay, but the point here is, this is how a materialist believes that the solar system formed. Okay. Uranium, lead, radioactive decay chain. I know you've been holding your breath for this slide right here. So unstable parent isotopes transform into stable daughter isotopes. Transformation occurs at a measurable rate, half-life. And for each half-life, 50% of the remaining parent isotope decays. And what we're interested in terms of dating, is the parent to stable daughter ratio may allow an estimate of elapsed time. So if you look on this graph I have here, up in the upper right, you see uranium-238. That is a unstable isotope. I guess I need to explain what an isotope is. What makes an element is the number of protons. And so on this graph that I have here, protons are on the x-axis. So you see the 92 on the lower right, 92 protons. So if you go up, you'll see there's a uranium that intersects on the y-axis with 234. That's the number of protons plus neutrons. And then if you keep going up, you see U-238, which again, the 238 is protons plus neutrons. So an isotope is just an element with varying numbers of protons or neutrons. Does that make sense?
Yep.
Okay. All right. decay. There's two types of decay that happens in U-238. Basically, two types of decay that occur when U-238. If you follow it all the way down, follow all the arrows down, and you see where it hits lead-206?
Yes.
Lead-206 is the stable daughter element. And there's alpha decay and beta decay on the way to getting there through these intermediate isotopes. Like if you had a Geiger counter, you would pick up these high energy electrons that are emitted during beta decay, for example. So again, the key message here is radiometric dating is going to kind of take this information and sort of, if there's a lot of lead-206, that would seem to indicate a lot of time has passed since it was originally U-238.
And that's because of the decay rate, right? And
yes.
So what is the decay rate for uranium lead?
Oh, it didn't show it. Okay. So I didn't put it on the next slide. U-238 has a half-life of over 4 billion years. And on this decay chain, what's real interesting is each of these daughter isotopes has a different half-life. There are some of them that have a half-life of seconds, some minutes, some years. U-234, if I remember correctly, is over 200,000 years, for example. And so these intermediate isotopes, again, have much shorter half-lives than U-238.
Great.
Okay. All right. So we want to use this this knowledge to date a rock. So if you look at over on the current side, and I've limited this just to isotopes that interest us in this particular isochron method, which is the lead-204, 206, and 207. We can see that in the rocks today. 204 is stable, lead-204 is stable. So we just assume that it's always been kicking around. So if we go back to the initial time, we would assume there must have been lead-204 at that time. So then the question is, we have all these isotopes, those isotopes I just showed you on the prior slide. Well, which ones are we going to assume that were present at the formation, at crystallization? That's sort of the question, the first question we have to answer with this method. And so I'm going to refer to this as Patterson's chronological model. I use that to mean the same thing as the lead-lead isochron model. Starts with a billions of years presumption. So if you think that the Earth is billions of years old, you select the isotopes with very, very long half-lives. And in this case, U-238, 4.47 billion years, and U-235, 0.7 billion years. And you ignore all the other isotopes that have shorter half-lives. That's step one. This little table on the right, this is just a little, I'm going to be referring to this 204 lead, which is stable, as a reference. And then, of course, U-238 decays to 206 lead, 235 uranium decays to 207 lead. So to answer that question that I just posed, if you look over here on the initial side, I've listed 204 lead, 206 lead, 207 lead, 238, and 235. So in other words, the two uranium isotopes that have very long half-lives are there. And we suppose that there was, at crystallization, this 206 and 207 lead, and that's referred to as primordial lead. You'll see a lot of papers, they refer to a lot of primordial lead. And in the transient time, the uranium-238, 235 decay into these stable isotopes. And that's called radiogenic lead. And in order to date, we have to know the difference between radiogenic lead and primordial lead. Because if we assume if we have some primordial lead mixed in, it's going to make our calculations erroneous. Does that make sense?
Yes. Mm-hmm.
Okay. All right, good. All right, here we go. We're going to get into the method now. Of course, I'm an engineer. I'm kind of partial to equations. So, of course, I had to put some equations up here for you. The governing equations where this starts is, if you look right under step 2, I've got U238 as a function of time. And there's just a simple equation that relates the original amount of U238 to time. The lambda is related to the half-life. We've already picked those 2 uranium isotopes. We do some substitution, some rearrangement. This is probably freshman level calculus type math. It's not particularly hard. And you get to a point with 2 equations and 3 unknowns. Here are the 2 equations that I've got here. You see 206 lead, which is what we measure today, and 207 lead, what we measure today. And then in red, I've colored the 3 unknowns. Over on the right, where you see that 206 PB in red, that's the primordial lead. And then you also see time in there. We're going to make a simplifying assumption that time is all the same, so we can count that as one variable. So there's, again, 3 unknowns, 2 equations, and at this point, we can divide it by this 204 lead as a reference and get the form y equals mx plus b. Because it's 2 equations, 3 unknowns, we can't solve it algebraically. So we have to have a graphical solution, make some assumptions here and there to get to the answer. So on the right, you're going to probably get tired of this particular graph, but it's going to be the same on each of the next slides. On the y-axis, on the x-axis, you're going to see a ratio of 206 lead to 204 lead. That's related to the uranium-238. On the y-axis, that ratio is related to the uranium-235. So this axis is going to be the same on all the graphs. The other interesting thing about this is the data, the isotopes that we measure today, like when we go measure rocks, when labs measure rocks, today's data is always going to plot on the same place on this graph. It's not going to change. Okay, so hopefully I've set you up here pretty good and giving you a little context.
Yes, you have. And I just have to put up this comment because this is just hilarious. Travis says, this slide lacks faith. Isn't that the first step? Yes. And I think so, right? In radioisotope dating, you got to have faith that the Earth is billions of years old first, right? So, okay, go on.
That's what one of the things I'll try to show. But all right, so step 3, here's the equation for the slope. And what's relevant here is the only variables in the equation are time, and this lambda. And so what I can do is I know the lambda for the uraniums. If I plug in 1 billion years, then I get a slope. And I plotted that over here on the graph. Do you see where I labeled 1 BYA?
Well, it's a little bit small for me, so I'll need my glasses.
Okay.
Okay. Yes, I do.
Okay. So then I can plug in 2 billion years and I get a number, I get a slope, and I can plot that out. And
Okay.
so I did that for 1 to 7 billion years.
Okay.
One of the things, and right now I'm going to ask you to take my word for it. Do you see where all of those lines cross? It comes right around 10 on
Yes.
the x-axis, 10 on the y-axis. Okay, that's the presumed primordial lead ratios. Just take that at face value right now. We'll talk about that a little bit later. But basically, that is an assumption of a presumption of what the primordial lead is. You have to come up with that somewhere because you have that in the equation. Okay.
Okay.
All right. This is where it gets interesting. Step 4, plot our current measurements. So I'm going to use Patterson's 1956 data all through here. The only thing that has changed since Patterson did this is the instrumentation. Our ability to measure using like AMS or that sort of thing is so much better than back then. The assumptions, the methodology are the same. So what I did, you see the red, I've got some dots here. Those represent individual asteroids. And
Yes.
you'll notice they plot on the same line.
Right.
And Patterson interpreted that as an isochron. And one of those red dots is ocean sediment. He used ocean sediment because that sediment presumably has been eroded from many different places, lots of high energy mixing, and it would represent a meaningful isotopic ratio. And so for Patterson, the fact that ocean sediment plotted on the same line as meteorite data was a very powerful argument in favor of his model. And I agree. I think that is the strongest argument for his model. So anyway, add the trend line and we get a slope. The slope of this is actually 0.6024, that red dashed line. And that correlates, you can solve it by trial and error, to 4.55 billion years ago. When I did this, I used a updated decay constant from 1973, which Patterson didn't have. And I got 4.52 billion years. So I get the same answers as Patterson does. All right. Now it's time to ask a few questions. What if the daughter isotopes were present at initial conditions? You remember how I said he ignored all the daughter isotopes? All right, so what I did here is I just included one daughter isotope from the uranium-238, one daughter isotope from the uranium-235 decay chains. So that's U-234 and protactinium-231. Because their decay, their half-lives are different, when I plug a time, or when I calculate a slope, I get a different time than I did when I was just using the parent isotope. So if you look over on the graph, the uppermost line has 1 BYA in parentheses. That's the exact line I had on the previous graph. But by including the daughter isotopes, that now calculates to be 500,000 years. 2 billion years is 2 million years. So you can see that the interpretation of those lines changes because I changed the initial isotopes. So if I take that to its logical conclusion, you see I've got Patterson's data, and I use Patterson's chronological model, the lead-lead isochron model, and I use all of his assumptions except I add 2 daughter isotopes. The Earth's age is 1 billion years with the same data. And there's no artifacts to reveal that I changed the isotopes. So in other words, as an observer, I can't be sure if this is really 1 billion years or 4.5 billion years.
So why was the 4 billion years chosen then?
Because now I'm not able to talk to Claire Patterson, and it's not fair for me to put words in his mouth. My assumption is he believed the Earth is billions of years old. And if you believe that, then you would tend to pick isotopes that have the longest half-lives. And what he would say, again, I don't know what he would say. What he might say if he were sitting here discussing with us is, well, you can't use U-234 and 231 protactinium because those would have already decayed between when they were formed. You remember the stars, and when they crystallized, remember the solar nebular hypothesis. That's what he would say, or likely to say.
Okay. I see. Well, and I don't want to interrupt with questions until you're with more questions until you're done with your presentation, but I do have a question.
Shoot.
Well, okay. So the one thing that I've heard about, and maybe this is where we get into the zircons, I don't know, but basically what I've heard is that the reason we can trust the uranium lead dating is because when uranium is formed, and I mean, when it's like in zircon crystals, it's not possible for the daughter element to be there. So it's not possible for the lead 206 to be there or whatever. I might be getting the isotope wrong, but it's not possible for that form of lead to be there. And so any lead that we find there is from, the nuclear decay. So
Zircon is the silver bullet. Short answer to your question is that zircon's acceptance or zircon's rejection of lead is conditional. And I've got 3 slides to address that coming up.
perfect.
You had asked me that in Colorado, so I wanted to make sure that we get that covered tonight. Okay, that is a great question. Hold that thought, we'll get to it. Okay, so all I've tried to show you is radiometric dating ages are non-unique. Now I want to just talk about a divine creation premise in the context of this particular methodology. So what I'll say is, if God created the universe. In the beginning, God created the universe, Genesis 1:1. Then that premise would probably fall along the lines that at initial conditions, he created all of the isotopes at once. All of the isotopes in the decay chain, everything was created. That's going to be my premise for the initial conditions. And so this next slide, there's probably 3 really important slides in my talk, and I think this is one of them right here. Look at this table, and there in red, I've got the divine creation scenario. You will recognize the slope. By the way, this is the slope from my data. It's just a little bit different than Patterson's data, but it's 0.6027. Those are the isotopes that I put into the model. When I use the methodology, I get 8,000 years when I calculate that date numerically. If I just do it graphically and I assume that it's only U238 and U235, I would think it was 4.52 billion years, even though I've numerically calculated it as 8,000 years.
I'm not sure I understand.
Okay.
Can you try to like break it down a little bit more? How, like, what are you putting into, or is this going to be explained more in the next slide?
No. This is a good question. We need to address it now.
Okay.
So right here, you see under presumed, Patterson's thought was you only had these 3 isotopes of lead in U238 and U235, and that's it. He gets 4.55 billion years.
Now, is the reason that he's thinking that is because of something related to the nucleosynthesis? Like, basically, he doesn't think that the lead would have been, synthesized in some way, that it all has to be a daughter product, or like, where is his assumption coming from?
Okay, his assumption's coming from, if you can imagine a star blows up and makes a bunch of uranium and a bunch of daughter isotopes. A billion or 2 years go by before that material forms into planetesimals. During that interval, these daughter isotopes, thorium, radium, protactinium, actinium, they all decay to lead. They're no longer present.
Oh, I see. Because it's been so much time, they would have been gone by then.
Yes.
Okay, I see. Mm-hmm.
Yes. Yeah. That's an excellent question. So that's what, and then if on the flip side, under a divine creation premise, we might take that God created all these isotopes at the same time when he created the universe, when he created the solar system. Therefore, they are present at crystallization.
Okay, gotcha. And is it possible for that to be like, if we're talking about in a meteorite, is that possible that all of these things could be present? Like, there's nothing chemically that makes that not possible?
I don't think there's anything within what we know that would make this an impossible scenario.
Okay. So now we're getting to this, and I'm still not sure that I understand this. So
okay, all right, we'll walk through it, and ask again. So let's start up here. The scenario, the first one is the materialistic scenario. This is all of Patterson's assumptions. And you see the initial isotopes, U-238, 235, using the graphical method, 4.52 billion years, using the numerical method, which, in other words, think of that as the Wizard of Oz behind the curtains, making all the calculations, all knowing kind of approach. So when I say numerical, that means I've actually calculated, because I've got the equations that I can calculate.
Okay.
Then I showed you this 1 billion years. I just added U-235, 231, uranium and protactinium. And the slope is the same. It plots the meter of data exactly the same. It plots on the same place. And numerically, I calculate 1 billion years. And I did not show you the graph for the 100 million year scenario. All I did was change the initial isotopic ratio, adding more uranium-235 and 231 protactinium. I can get 100 million years. And then,
but let me the thing I'm not clear on is, like, is the materialistic one where Patterson was plotting it based on what was actually found in the meteorite and in the other, I think you said the deep sea sediment, but he just ignored the other stuff? Like, all that stuff was present, but he ignored all those other isotopes?
so in the current, all we can measure all the isotopes that are present today, but what's germane for lead isochron is 204 lead, 206 lead, 207 lead. That's all we're measuring today. So for each scenario that I listed on that table, these are the only 3 isotopes that we're measuring.
Okay. I see.
My initial assumption is what causes me to calculate a different solution.
Okay.
So that's why I say that lead dating yields non-unique ages. Another interesting thing is lead dating ages, depending on my initial condition assumption, they're consistent with both materialistic and divine creation worldviews. I can't distinguish them. I can calculate using Patterson's methodology, except for the initial isotopes, I can calculate 8,000 to 4.52 billion years. And I'm of the opinion that you can't tell the difference. You can't tell. We don't know. We have no factual, measurable, observable data on the initial conditions. We don't know. Everybody's spitballing on what this is. We have no factual, measurable, observable data on the transient conditions either. Everybody's spitballing on this as well. And so the implicit message is the range of uncertainty should be extremely high. And I think when we do the math, we get an extremely high range of uncertainty.
Wow. Well, now the question comes up for me. How is this being put forward as such solid evidence of the age of the earth when there are this many assumptions going into it?
I would say when we sit down at the table of the buffet of confirmational bias, we might get part of an answer to that. So we'll try to cover that here at the end. I think when we wrap it up, we'll try to address that question.
Okay.
All right, so here I'm showing you a similar data set, different format, but the same conclusions. So if you look over here at the graph, you'll recognize those points, the meteorite points and the ocean sediment points. Now, what Patterson said, I'm giving you a little more detail I'm going to give you more detail on his assumptions as we go on, is that everything formed from a single reservoir, assuming an initial primordial lead. And he measured that lead, and I'm going to talk about it. And that's that point that's the furthest, it's about 1010. That point's going to keep coming up because it's very important. And so what he thought is, if you can imagine, that's the starting point. And then as time goes by, that's what these dashed lines are. So as time goes by, that you can see that 4.5 billion year line. That's how that this isotopic ratio, how it changed with time. Initially, the U-234 was decaying faster, which pulled that slope up, if you will. And then as it fell off, more of the U-238 was evolving into lead, and that's why that line moves over to the right, if you will. And so each of these dotted lines represent one of those scenarios I just showed you on the prior slide. So this is numerically what's going on behind the scenes, if you will. And the thing is, you've got all these lines. Pick one. We have the initial conditions problem. We have no factual observations. We have no factual data at initial conditions. We have a transient conditions problem. We have no factual data, no measurable, or no observations, no facts for transient conditions. We can't distinguish. And so if you were to say, well, Vann, what would you need to know for you to accept this method? What I would need to know is what happened at initial conditions. What were those initial isotopes? And if I knew that, I would have a pretty good chance of being able to calculate the age, knowing what we know today. The reason I say pretty good is because there are some things that can occur during the transient that would throw my calculations off. But I would, if I knew what was going on in initial conditions, I would know that I had a problem. Of course, that's not possible. So again, these are different paths. Pick one. So again, this is trying to show the data in a little bit different way to give you a little bit better idea, and also to highlight this Patterson single reservoir assumption, that there was a single reservoir down here. This, by the way, this meteorite is the Canyon Diablo meteorite. Do you know that very large crater in Arizona?
Yeah.
Okay. A piece of that impact is what Patterson is using to anchor his model as the primordial lead. And again, I'm going to talk a little bit more about that. So again, I think the point of this slide is to reinforce the uncertainty. All right. Zircon. I mean, that sounds like something that Superman should use to make him stronger or something, the anti-kryptonite. But anyway, we're going to talk about zircon, and I'm going to suggest to you that the real question revolves around trilite. Okay. Now, what I'm going to share is, this is no news to materialists. If you look over here on the table, you can see the event. And I've listed volcanoes because typically I'm switching a little bit from dating meteorites to volcanoes simply because on these volcanoes I've listed here, we actually know when they erupted. We actually know the answer. And so I've got the event date, and then I've got the radioisotopic age. And I went ahead and I put the method. These use a little bit different method. Generally, the assumptions are the same. So what we're talking about conceptually is the problems with lead are going to be the same problems with argon, and potassium, argon. So and let me first say, this is not a statistically representative sample. This is probably Vann's conformational bias right here. Vann went out and looked for the ages where the radioisotope age was just totally wrong, just to make a point. So I admit it.
Well, I do have to say that I recently read a paper where basically the researchers took all of the data that's in the US database on things, that we've dated in this way. And the vast majority of ages did not agree with each other. When there was more than one type of dating used, they very rarely agreed with each other. And there were many dates that were off. So I'm not going to say that you did this by confirmation bias, but hey, if anybody wants to present times when we can be sure that these dating things are accurate, like the Mount Vesuvius, great. Put it in the comments and I'll talk to you about it. You can come on my channel and talk to us about it. Okay, please continue, Vann.
Perfect. So, I don't need to explain this, right? 21 million years ago, it had, in Hawaii in the 1800s, 2 million years ago in Alaska, that sort of thing. So we know these dates can be inaccurate. Well, why is that? Well, the initial conditions problem, in the case of lead, this unknown isotope distribution that we've been talking about so far, that's the only thing we've been really talking about. This primordial lead, we're going to get a little bit more into, and then this transient condition problems. All these dates assume that a closed system, that there's no loss of isotopes, there's no loss of lead or uranium isotopes or daughter isotopes, and there's no gain of isotopes during that intermediate period. So,
but before you go on, I do want to explain the chart to those who are not familiar with this, okay? And I'll just state it simply. What Vann has got here is times that we have tested rocks of known ages, and the radioisotope age comes out to be millions of years. So the event, like the Mount St. Helens event, we know that Mount St. Helens erupted in 1980. When rocks taken from Mount St. Helens were radioisotope tested, they came out with ages that were in the millions of years. So this is a rock of a known age that's coming out with a very wrong age, and that's what he's got. With all the things with the red X's are times we've known the age of the eruption. So we know the age of the rock, and yet it comes out as Mount Kilauea in Hawaii came out as 21 million years old, even though it's only a 150-year-old rock, or I'm not sure what the exact age, you just have 1800s there, but
Yeah.
So yeah.
No, thank you. That's a great explanation. And I did give a gold star for Mount Vesuvius because there was one that seemed like it came out pretty good. All right, that's a
Cool.
good explanation. Thank you for clarifying that.
Yeah.
All right, zircon. So the initial and transient problem is loss or gain of isotopes, and then also this primordial lead. So radiometric dating attempts to measure radiogenic lead. That's the lead that decays, say, within a zircon crystal. And primordial lead or transient changes in lead result in an error. So zircon is said to reject lead into its crystal lattice. Think of you remember when I was a kid, you had a tray and you put water in it and you put it in the freezer and then you pull it out and break it and you had your little ice cubes that you would dump into your glass. That's water crystallizing into ice. And so what we're talking about with zircon is it going from a plasma to a crystalline structure. And in that crystalline structure, there's a zircon atom, there's a silicon atom, and there's 4 oxygen atoms. And what's interesting about zircon, and this is why, like Rebekah, this is why you hear about zircon. It's got a really high melting point, very high. Like if it was in the Earth's crust, you could metamorphize it and it would still be a crystal. It's pretty seriously hard. 7.5 on the most hardness. Diamond is a 10. Gold is around 3, just to put that in perspective. And it generally has a pretty dense and stable lattice. So yeah, in the Earth's crust, zircon does look like it rejects lead, or it does reject lead. However, let me just talk a little bit about why that is. If you look over here at the table, I'm just going to give you a couple reasons that have to do with the incorporation of a atom into a lattice. I've got the element, the charge, and the ionic radius. And so zircon has a charge of +4. Its ionic radius is 84. Uranium will readily substitute into that lattice. It's called isomorphic substitution. And it does that because it has the same charge, +4, and its ionic radius is pretty close to that of zircon. If you go down, do you see where it says where I have lead 2+? This is the most common type of lead in the crust. It has a charge of +2. It has 2 more protons than electrons. So it's not, in terrestrial setting, it's not going to substitute into the lattice for zircon because it's got the wrong charge. And then look at the ionic radius, 129 versus zircon at 84. So what you're hearing and have heard is true. But if we're going along with the stellar nebular hypothesis, we're gonna have to assume everything was a plasma. And a plasma, high radiation, electric magnetic fields is going to tend to strip off the 2 outermost electrons in lead. Look what happens. Lead then gets a charge of 4+, and then its ionic radius decreases. It's got more, there's more the ratio of protons to electrons pulls that atom tighter together. And under extraterrestrial conditions in a plasma, it looks like lead will substitute into the zirconium lattice. And so that's why I say conditional acceptance of lead into the zircon lattice is because I'm assuming, going along with Patterson, that it had to have been a plasma. And in a plasma, you're going to tend to have all these ions floating around with a lot of electrons. And so having a lead with a charge of 4 is not unreasonable. And that would likely substitute into the zircon crystal. This is not a area of expertise for me. And I've listed 2 things that determine this isomorphic substitution. There's probably 3 others, but these are the 2 seem to be at the top of most people's lists. So again, conditional acceptance. All right. Now this one's a tough slide. Let me try to walk you through it. I can see your eyes rolling. Oh no.
Oh no, I'm loving this. I'm loving every minute of this. Go for it, Vann.
Okay. Uncertainty and inconsistency is the point I'm going to make with this slide. Zircon at initial conditions. The materials paradigm is that it rejects lead. Therefore, we don't have to worry about primordial lead when we do our dates. Therefore, our dates are all correct because we're dating zircon. That's the thrust of that particular argument. Well, I've just talked about the conditional acceptance of lead with a charge +4 into the lattice. And then also, lead may be incorporated into non-lattice positions. The lattice, when it forms, isn't perfect. So it's impossible to incorporate lead into non-lattice positions. Then at transient conditions, these are the mechanisms that either gain isotopes, whether they be daughters, lose daughters, lead, uranium. Leaching along the edges, edge defects, incorporating isotopes. The isotopes will incorporate into microfractures. And by the way, all of these are observable. This has been observed. We know this happens. This isn't just science fiction. Uranium decay, when uranium decays in the lattice, momentum is conserved. And so when it pukes out a helium atom in alpha decay, that will damage the lattice. So you've created damage where either the uranium can escape or daughter elements can escape or something else can get in. So again, there's uncertainty at both initial and transient conditions. Troilite. This is the anchor of Patterson's arguments. Troilite rejects lead in its lattice. The lead is just, it has the right charge, but its atomic radius is too big. Patterson found lead in troilite, in that Canyon Diablo meteorite. He assumed that lead was incorporated at initial conditions. Do you see inconsistency in the argument that you're sort of told, like, well, lead's not going to be incorporated, zircon at initial conditions, but yet Patterson made this argument that the lead he observed in the troilite was incorporated at initial conditions. And he assumed that all the lead he saw in it was only from initial conditions. He totally ignored the possibility of lead incorporation at transient conditions based on those mechanisms I've listed there on the bottom left. And so he used this troilite lead measurement as an anchor for his method, that place where all those isochrones intersect on those graphs that we were looking at. That's where that comes from.
Okay, wait, I'm trying to put this together. Okay, so can you remind me that point on the graph, he's using that as an anchor to like show how much lead should be there?
How much lead at initial conditions, primordial lead, because
Okay,
he's got to have something for that in order to even draw these isochrons.
I see. Okay, so he's assuming because the trol trilite, how do you say that?
Troilite.
Troilite, that it normally rejects lead, but he's not taking into account all of these things that you're saying. So he's saying, okay, we know the initial conditions, and therefore I'm using the amount of lead that's in the trolite as my initial conditions.
Yes, he's assuming that the lead that he found in the troilite, which shouldn't have been there, according to your normal rule of thumb, he's assuming the lead he found there was only and entirely due to being formed at initial conditions.
Okay, yes, I see.
See, he had to make that assumption in order to get somewhere to anchor his data. And by the way, those ratios, well, that's what's used in today. That's what the isochron method will start with. They'll tweak it, they'll let it range a little bit, but that's basically still in use today. So this is a critical assumption.
Wait, you're saying they're all using it from Patterson's initial thing?
They're all using a very similar uh, primordial lead ratio when doing age of the earth calculations.
Did they source it only from Patterson, or have they like sourced it from other places now? And it's okay if you don't know the answer to all
Yeah,
this.
yeah, yeah, yeah. I'm trying to remember back to a technical paper that I saw. They have found a similar ratio in some other places. I can't speak to how many, if it's just
Okay.
one or more. So that's probably something to follow up on.
And these things that you've listed here, the possibilities for things happening in the transient conditions, have we shown that these things can happen, or is this something that's too difficult to test? Or, I mean, like, what's the state of, do we know that this happens?
These have been observed, at least these mechanisms, but I don't know if they're specific to zircon. I know that in terms of crystals, these mechanisms have been observed.
Okay. Cool.
So
Amazing stuff,
again,
man. Thank
okay,
you.
good, good. So the uncertainty, and again, I just want highlighting a little bit of the inconsistency because, again, people will say, well, zircon rejects lead, therefore our measurements are right. But over here, uh, Patterson assumed that the lead he saw, which should have been rejected, was actually incorporated at initial conditions. Do you see the inconsistency there?
Right.
Okay, good. All right. All right. So this is probably another most important slide right here. And we've kind of had, and I apologize, I'm taking so long. We've kind of had to go through all that other stuff to sort of get to this point, because this is how, like, if we're conversing about this, I think this is the things that we need to talk about. So Patterson's assumptions, he assumed that linear data, which again, I think that's the strongest argument in favor of his methodology. He assumed that linear array represented chronology. It was linked to time. In terms of the initial condition problem, he thought that everything, the Earth and the asteroids, meteorites, all formed from a single reservoir at the same time, and that the lead, the primordial lead, was homogeneous in that reservoir. He thought that no matter where we go, we're going to have that lead as the primordial lead concentration. Now, we could probably dispute whether or not that's a reasonable, it's probably 50-50 whether it's homogeneous or not, or who knows. But one of the issues I see is he assumed that even though it was a single reservoir, he assumed that the uranium isotopic composition was heterogeneous. And it sort of is an inconsistency to assume, well, the lead's homogeneous and the uranium is heterogeneous. And the reason that I say that he assumed a heterogeneous uranium composition is because you have today, we measure different amounts of lead and uranium in these different meteorites. So the only way it gets that way is if the initial uranium isotopic ratios varied within the single reservoir. So that's a significant assumption. And we've already talked about at length that he assumed only U-238, U-235. Of course, the transient condition problems, he assumed it was isolated in a closed system. And that prior slide we were just discussing, we can see that there are mechanisms. We know there are mechanisms for it not to be a closed system. So to me, if you go back to what Sherlock Holmes was saying, his result is 4.5 billion years. And then these are the most important links in the chain in order to get to that result. Okay. All right. Now, I'm going to totally switch gears on you, but I'm going to use the same data and the same graph. Okay. And what I just tried to show, just looking back, was that zircon doesn't solve the initial or transient condition problem, is one of the points of what I was just talking about. Okay. Again, going back to Patterson's 1956 paper, he said the data can be explained by other qualifying or even contradictory assumptions. Now, I've shown three glasses here. One of them looks like it has Coca-Cola in it. I don't know if I want to drink it, but that's what it kind of looks like. The middle glass is empty, and then it looks like there's a clear liquid, perhaps water, in the third glass. Now, what would we see, Rebekah, if we mixed them 50-50?
Well, it would still be brown. It would be brown if we mixed them all up.
Yeah. Would the color, do you think the color would be different?
Lighter brown, probably.
Yeah. We would have an indication that there was mixing. And then if we were really smart, we could calculate the fractional percentages and we could verify that sort of thing. So that leads us to the binary mixing model. And what I'm going to say is the binary mixing is inconsistent with Patterson's chronological model. So if you look over, go ahead.
But can I ask you before we move on from this slide? Sorry, I moved it back. Okay, what does he mean when he says the data can be explained by other qualifying or even contradictory assumptions? 'Cause that seems like a really weird statement to put in a book where you're, or a paper where you're trying to describe your findings. So what does he mean by that?
He's saying that there's other explanations. Did he have binary mixing on his mind when he wrote that? I don't know. He was obviously a brilliant guy, and I would suspect he would have been aware of something like this, but I, I don't know. Like contradictory assumptions, I'm gonna on this mixing model, the contradictory of what I'm saying is it has nothing to do with chronology.
Okay, cool. Okay, I'm ready to go on.
Okay. All right. So if you look at the graph, purge chronology and dates from your mind and look at it this way. We've got a line, the binary mixing line, and there's two endpoints. One is the Canyon Diablo troilite, which we've talked about. The other one is this meteorite that landed in Mexico. When we look at this, we might be inclined to say, well, this represents a mixing line. And there were two endpoints. In other words, there were two reservoirs. One was this, represented this Mexico meteorite, and the other, the Canyon Diablo troilite. And what we find in between is just simply some amount of Coke and some amount of water into the glass, and you get Iowa, Kansas, and ocean sediment, and also the Australia. All of those fall on the line in between Canyon Diablo and Mexico.
Okay, awesome. I see what you're saying. Yeah.
Okay, good.
Yeah,
So
I get it.
So, and again, not a field of expertise for me, but I did do 3 checks observationally to try to verify this. And I've listed there the cross isotope fraction agreement, the free axis linearity, and ratio of ratio curvature test. I didn't include the plots because we're already taking a long time. Maybe we do this on a different talk. I can go into that. The point is, on this binary mixing, there are some standard checks that can be done. And if any of them are false, then we do not have binary mixing. And so I've done 3 tests, and they are all yes.
Okay,
So
wait, hold on. Before you go on, I want to make sure I'm understanding, because I did just have something pop up in my mind that, okay, from my understanding, and I could be misunderstanding it, but so the plot shows, like, basically the reason it's all along a line, putting chronology aside, but like, is that the ratios are the same. And so if it's like an outside lead that somehow got in, then it wouldn't plot along the line. So this is kind of showing that it's a pure, like, ratio, like that it came from basically it's a parent-daughter thing rather than contamination from outside. So that does that factor into what you're saying here?
to say it another way, this is there's no effects of transient or initial conditions. This is just what we see today.
Okay.
Or this is an alternative explanation for the point that's most in Patterson's favor, which is the linearity of his data set.
Okay, so you're saying this is like something like it's showing that it's not from contamination.
It's all out the window.
Wait, what's all out the window?
This is what it is. Like the two reservoirs. One of the reservoirs was the composition of this Mexico meteorite, and then the other reservoir was just the composition of that Canyon Diablo troilite.
Okay. Mm-hmm.
Yeah, this takes it's a totally different paradigm.
Okay. And so what are these yeses here?
Okay, so three-axis linearity, what you do is you plot, you keep the 206, 204 x-axis the same, and on the y-axis you plot the daughters of thorium, which he gave some thorium data, Patterson, in his paper, uranium-238, U-235, on three different plots, and then you look at them and see, do they line up? If the answer is no, then you tend to think, well, this is not binary mixing. If the answer is yes, all three plots are linear, which they are, and this is one of those plots. This is the basically the 235 daughter plot right here. So imagine doing that for 238 and then doing another one for thorium.
Okay.
They're all a straight line.
I got it. Mm-hmm.
So, and then the cross isotope fraction is a mathematical calculation, and then this ratio of ratio curvature is just a little bit different plot. I believe there's some more tests that one can do on the data, and again, maybe that's something we need to look at. But right now, I can say I checked it for three different things, and it was positive on those three different things.
Okay. So I'm still trying to understand, like, okay, can you like explain what are the things that would make like these three yes things? Like, what is this tell? What did you do? What did you test? Like, what are you seeing here?
It's kind of like if we had, you remember those three glasses, and we had Coke and we had water in one. Say we had another glass that had something else in it. Say it had Sprite, and we dumped them all three in there, and we did these three tests on it for binary mixing. We would not get a yes to all three of these tests.
Okay. But if it is binary mixing, we would get.
If it was binary mixing, we would get a yes to these three. Plus, there may be some more that we can look at to confirm that.
Okay, I guess I'm just trying to see how, and I don't mean to make this like way longer than I'm just trying. I really want to understand this concept. So I hope I'm not messing us up right now. But what, like, so let's just say we mixed those three. How would we be getting this plot? Like, what would that, because we mix the same things, then I wouldn't see us having this plot right? I would see it being like all the same.
In
Or
terms of
am
the
I wrong about
glasses,
that?
or all right, let me spin it around. Mexico had a unique isotopic concentration of uranium, lead, thorium, all those isotopes.
Okay.
Canyon Diablo had a different
Got it.
concentration. And then if we mix those two together, depending on how much of Canyon Diablo and how much of Mexico we placed into our empty glass, would be where we would plot on this binary mixing line.
Okay. I'm not still sure I'm understanding, but I hope those who are out there who know this stuff can understand it. So,
And I'm hoping, that we'll get some conversation on this particular point, because as I mentioned, this is not a field of expertise, and I would certainly like to hear from some of our evolutionary friends or creation friends that have a different perspective on this. Where I'm going with this is, if binary mixing is true, then Matt Patterson's chronological model is false, because the binary mixing assumes two different and distinct reservoirs, whereas Patterson, for his initial condition, is assuming one reservoir with homogeneous lead.
okay, interesting.
And the other thing on this is, I didn't get a chance. I haven't done a complete literature search. Somebody may have already barked up this tree. And so again, maybe with some of your viewers who have more expertise or have seen this before, maybe we'll be able to learn some more about this.
Yeah, and if there's anybody out there watching this that has something to say about it, we would love to have a further discussion. So please do contact me, send me an email, and we'd love to, like Vann said, continue the conversation. Okay, so do we have more assumptions, suite of assumptions here? Confirmation
Nope.
bias buffet?
Yeah, that's where we're going. That's where we're going. So what I said here is binary mixing may. Notice how I use the word may explain Patterson's meteorite data. So, all right, confirmational bias. Confirmational our worldview acts as a filter, and our worldview sort of causes us to let in information that supports our worldview and to deflect information that challenges our worldview. A biblical worldview person as myself, I have to be careful of confirmational bias, just like our materialist friends need to be aware of confirmational bias, because it's easy just to say, well, how do I prove my belief, and just leave it at that. All right, so soft tissue, you've covered this before. The only reason I'm sharing this is because I thought this was an interesting find. This ichthyosaur, which is this creature there I've got on the right, there's a fossil of it actually having live babies, by the way. There was a paper from Lund University in Sweden, and they said that they recovered still flexible remnants of original scaleless skin, distinct epidermal and dermal layers. And they found blubber. And so this gave them the indication that this creature was warm-blooded. And because the skin, they could see the pattern on it, it gave them an indication of what kind of camouflage pattern was on this creature as well. So anyway, this was kind of a neat paper, I thought. So, and I know all of your viewers are familiar with soft tissue and dinosaur. I mean, you
Well,
guys
I
have
don't know who watches, so we don't even know. But for those who have not heard about this, one of the things that contradicts the idea of these creatures living millions of years ago and all the dating that you've been told about is that all of this soft tissue has been found in fossils that are supposed to be 100 million years old, various ages. And there's no way, scientifically, by our scientific observations, there is no way these types of things can last that long. So this has been confirmed over and over again. And actually, I talk to people about this, like at my workplace and different, I talk to people about this all the time. And it shocks me. Most people have never heard this. And, you know, you always hear about the latest things going on, you know, with scientific discoveries. So why is it that this has not been widely shared? Why is this such an unknown thing in the public? You know, anyway.
No, that's a great question. I mean, this was discovered by Mary Schweitzer in 2005. That's 20 years ago. Okay.
Yep.
You're right. Okay. So, okay. What does ice cream, Vann, and T-Rex have in common?
Carbon-14.
Carbon-14. Touchdown. That's right. Carbon-14. Again, you guys have talked about this on your channel. Carbon-14 is a radiometric isotope. It has a decay life of 5,730 years. It's in all living creatures. And when creatures die, that radiometric isotope decays. So if something is millions of years old, it should have 0 carbon-14. Now again, and carbon-14 is found in coal, it's found in dinosaurs, and again, just to add to the conversation, because you've covered this before, this is nothing new. There's a 1961 paper that acknowledges the presence of carbon-14 in coal. This is nothing new. And so, well, how did it get there? Well, groundwater deposits may have deposited carbon-14 in the bone. So the labs have known about this for 60 years, and so they have a very robust methodology that they go through on all the samples in order to try to get rid of this contaminated carbon-14. And often they'll after they go through acid and base washes and that sort of thing, they'll have like 10% of the original sample. And then they'll run it through the AMS. So this is a bit of a problem for our materialist friends, because if they reject carbon-14 in dinosaur bones due to something unknown happened during the transient, well, the problem is the labs have known about it for 60 years and have taken these steps to try to deal with it. Also, the other thing a lot of the labs will do is they'll report percent modern carbon in their findings. They will back off a estimated amount of contamination. They've already backed that number out, and then they show you what they think is the percent modern carbon. So again, you guys have covered this, and but it does merit a little bit of consideration that this is not a new problem.
Yes.
Okay.
And, you know, again, just because I've covered it before doesn't mean that the people watching will have heard this. So we're saying if you accept radiometric ages in the billions of years. What about this carbon-14? Do you accept carbon-14 radiometric ages? Because if you do, that absolutely contradicts the billions of years, or at least the millions of years for the history of life on Earth. So carbon-14 contradicts millions of years for life on Earth, period.
Yes. And this is Vann's opinion. I don't think that carbon-14 yields quantitative results because of trouble with initial and transient conditions. I think it is just a yes or no. It's either there or it's not. And based on the sensitivity of the measurement instruments, and depending on how much carbon-14 was in a creature when it died, 50 to 100,000 is sort of the age it could be. But I wouldn't try to qualify it any more than that, if that makes sense.
Yeah, absolutely. Mm-hmm.
Okay. All right. Thankfully, we've arrived at the second to last slide. The bias, or the buffet of conformational bias. So dinosaur, let's start at the bottom. Dinosaur soft tissue. There were some initial conditions on when it was laid down. Was it buried anaerobically? Whatever. There's the transient conditions. Did groundwater flow through it? Whatever. But the result is we have soft tissue. Now, the parsimonious explanation for this is that the tissue is not that old. And we know that from empirical observation. And then on the carbon-14, again, like what I hear materials say is, okay, we don't like the answer that there's carbon-14 there. Therefore, something happened during these transient conditions. And they're saying the same thing. Well, we really don't like that we found soft tissue in dinosaurs. Therefore, something must have happened in these transient conditions. And so materials will object to these findings based on these transient conditions. And so it appears that they have some conformational bias going on because they don't seem to have any trouble accepting our friends here, even though the uncertainty is greater than with the carbon-14 and the dino soft tissue. So it appears to be inconsistent, the logic, and it does appear to be a clear example of conformational bias to accept the uncertainty of our friends. You can't get away from these guys, by the way, when you're dealing with ages. I mean, they're kind of like, you know how you get peanut butter on your fingers, you can't shake it off? That's what these guys are like right here. You can't get away from the uncertainty. But again, the materials seem to accept this without question. But then when there's a result that is contrary to their worldview, it's a real struggle. And the fallback is, well, we've got to find something in the transient to explain it.
Right. But with lead, no questions. It is what it is. No contamination, no problems.
Exactly. All right. So to wrap it up, age of the Earth is unknowable using radiometric dating. The dating ages are non-unique. The ages are consistent with both materialistic and divine creation worldviews. Zircon does not solve the initial or transient condition problems, and binary mixing may explain Patterson's data.
Awesome.
And We've reached the end.
That was an amazing presentation, Vann. Thank you so much. Okay, do we still have time for questions?
Sure. And I
Okay.
apologize to your viewers for taking so long, and appreciate you guys for bearing with us for so long.
Oh, I love it that you're taking a long time on this, because actually, it's hard to find good information on this. And even from secular sources, there really aren't a lot of videos that explain this. So the first question that came in was from Junior Silva, and he wanted to know if you know about the Proton 21 experiments. And okay, so I'll answer that one. So that one's about in Ukraine, there's a lab, the Proton 21 lab, and I'll put up his answer. He said they produced results of daughter isotopes in the same ratio as Earth's ratio. Amazing proof that they were created catastrophically. So basically, like when they synthesized element isotopes in the lab, they got a mix of the parent and daughter of various radiogenic elements. So it's pretty interesting. So, and I think there's also a US lab that has done that as well. The Proton 21 lab, unfortunately, because of the war, is now shut down. But I don't remember the name of the lab in the US. But anyway, it's just kind of an interesting finding. So now Aprender says, I'm curious about what you exactly don't accept about radiometric dating. I hope you got your answer, and I hope this was helpful to you in some way. So let's see. Now, Andrew wants to know, does the guest have any geochronology background specifically? What would you say about that? Because you have a lot of knowledge. How did you get this information? I mean, was this just on your own study?
Yeah, I mean, as a petroleum engineer working in oil and gas, I worked with geologists, petrophysicists, geochemists, a lot of different disciplines. And I guess that's where I initially got the interest in it. And so through years of study, that's where I came to put this together, because I'm with you. It takes a lot of digging to sort of figure out how to understand it. And Patterson's paper is the key. Just everything you need to know is in Patterson's paper.
That's good to know. Thank you. Okay, and Andrew Cummings said, what does he mean by calibrated? This was toward the beginning of your presentation. So do you know what he's referring to?
Calibrated. I'm not sure what I said relative to calibrated.
Okay, sorry, Andrew. We'll have to go back and watch. But
thank you for asking. That's
yeah. So okay, and some of these are comments, but I'm kind of interested in some of these comments, so I started them. North Texas Fossils said, I hunt for fossils, and if not for the reliability and predictability of the geologic column, I would not be able to target the specific fossils I want to find or predict the fossils that I will find. You do have some probably experience or something to say about this, so I'd like to hear your thoughts.
Well, yeah, I mean, I think the way I interpret that comment is it's a relative basis, right? Like if I know what the stratigraphic column looks like in New Mexico, and I can correlate it over to Texas, and I know what fossils are found, and actually the fossils can help me predict what sedimentary layer I'm in, that gives me some ability to predict where to find fossils. So I'm assuming that it's not necessary to know the absolute age. And I can say that from experience, because you may find this hard to believe. when we cored, like when we drilled wells, say an exploration or a step out well, and we cored them, we would pull the core out and lay it down, and specialists would come in and look at it, and they would look, and they were specialists in little shells, and they could distinguish what kind of shells they were. And that helped us to know where we were in the geologic column by where those shells were. We didn't need to know the absolute age. Like in my office, I've got a core from the Dakota in New Mexico, and it shows bioturbation. So there's a whole field of people that specialize just in what North Texas fossil is talking about.
Okay. And so now for you, is that something problematic for your view of Earth's history and things like that? Is the stratification a problem?
No, I don't think so.
Okay. And this is kind of a continuation of his comment. Every layer where they can be dated always slot between older and younger dated layers. Even if you magically shrink the time ruler, faunal successions and radiations are still evident. Do you agree with that comment?
Wow, there's a lot there. I think I'd take a bit to absorb this one. If I understand what North Texas fossils are suggesting, is that you've got, when you date these layers, they line up. I think that's what he's saying. Like if you have an older and a younger, or a younger and an older that you've dated, and you date the one in between, it lines up in between.
Yeah, I don't know.
Is that what?
I'm not sure. So North Texas fossils, please leave us a comment and explain, and then maybe we can respond to that later, like, after the show or something. Leave a comment after the video. So Travis is saying, so is Vann saying the Earth is older than 6,000 years old? Can you ask him that? Because you had 8,000 years. So do you think the Earth is more like 8,000 years, or was that just an example? Like, what are your thoughts about that?
Okay, Vann's opinion is the Septuagint, in terms of the chronology, may provide better dates than the Masoretic. I would suggest checking out Henry Smith. He's done an awful lot of work on this particular topic. So do I believe it's 8,000 exactly? It's under 10,000, right?
Yeah. And so for those who are not familiar with what Vann is talking about with the Septuagint, so the Septuagint is the Greek version of the Bible, and it was in use very early on, and it had different dates, okay, than the Masoretic text of, so basically the Hebrew text, okay? So the early Greek Old Testament has different dates than the Hebrew. And they're about off by, I think, like 1,500 years, maybe. So it would like push the date of the flood back, which works kind of better with a lot of different historical events, maybe like the building of the pyramids and such. So I think I'm on board with you, Vann. But so essentially there's sort of there's room for interpretation with the age of the Earth. And by the way, if you're a Christian watching this and you think, well, the Earth can't be that young, I mean, I totally understand. And there's lots of people who reject evolution and still believe in an old earth. And you can do that as a Christian. Hey, you can even be a Christian and believe in evolution. I don't know why you'd want to do that, because all the scientific evidence is against evolution. But I do understand that for a lot of people who've been raised with, basically taken on this deep time of billions and millions of years old, that's a very hard thing to kind of get away from.
Just, I guess one more thing with respect to what Travis is asking. I did run a scenario that yielded 6,000 years as a radiometric age. So it's possible. It's with Patterson's assumptions in the initial isotopes.
Okay, right. So you're not being absolute about it. You're just saying it can fit whatever data you happen to already think. You can make it work with the ages. Okay, so Andrew says, I'm still confused how he calculated these dates using the same ratios and the same half-lives.
Okay, in the numeric model, I added a larger amount, say, one of the daughter isotopes, and that would result in a shorter age. So the ratio isn't the same, but the half-life is the same under initial conditions.
Okay. And by the way, if you're putting questions in now, I'm not going to see them. I'm only going with what we've already got. Okay. And I do have one from Howard toward the bottom, so I'll try to get to that. Okay. Wesley Coleman says, has he covered zircon crystals or helium diffusion? We didn't talk about the helium, so maybe we can talk about that on a different time. Do you want to say anything about that, Vann?
Let's try to hit it up at a different time. And on the helium diffusion, I believe Wesley's probably alluding to, does the helium as a daughter escape?
Yeah. Okay. Proper FPV says the age of the Earth is not based on a single measurement, but rather on a convergence of evidence from multiple scientific disciplines and techniques. Do you want to comment about that?
Yeah, fair enough. I mean, like there are some that interpret ice cores as being as simple as reading the rings on a tree, and you can derive an older age of the Earth from ice core data. There are others that look at the same data with a different worldview and interpret it as a much shorter period. So ice cores is certainly another, and I assume that that's what proper FPV is talking about. And he can probably think of a number of other lines of evidence that someone might use to support an older age.
Okay, Travis, it is not real serious question, but what assumption would Patterson have to make to conclude that the world is 6,000 years old?
I love it. He would make the same divine creation presumption as I did in order to make the math work, if he were to go down that route.
Now, Howard and by the way, Howard is a geologist, and he works in the oil worked in the oil industry for many years. So, you have some things in common. But he said you can't get a reliable C14 date from a dinosaur bone that has been exposed to weathering or groundwater for thousands of years. The same for coal. It is hopelessly contaminated.
The response to that is, okay, if we're going to throw out dinosaur bone and coal, then we have to throw out C14 dating for everything.
And what should we also throw out the lead dating, since it has all these problems as well.
Yeah.
And the point is that if, if these things are millions of years old, shouldn't we be able to find something, anything that, is carbon based that doesn't have carbon 14? And even diamonds, which are basically impenetrable, you can't contaminate them, have carbon 14. So yeah, that's a problem. And Howard says, how do you explain all the fossil soils and coral reefs scattered across the stratigraphic record in AM? I don't know what that is.
No, I mean, Howard, I think that a majority of the evidence supports a global flood. However, I've got some questions. How did we form 1,000 feet of limestone, the cliffs of Dover? How did we form that? How did we form salt domes in Louisiana? So that's a good question.
So you don't have all the answers.
I do not have all the answers. And I would like to talk to Howard about that and get some of his thoughts for sure.
Cool. Well, I would love to set up a talk with you and Howard, because I would love to just hear the interactions. I think you probably have a lot of the same knowledge and background. So, well, this has been amazing. Thank you so much, Vann. Do you have any final thoughts you want to share?
No, thank you for inviting me on your show. This is very exciting, and I wish I hadn't taken so long, but thank you for your forbearance and also for the folks watching.
Thank you. And it wasn't too long. I mean, I have no time limit on this channel. I loved hearing everything that you had to say tonight. Was very valuable and worth the time. So thank you very much. And I hope we can do it again. Thanks everybody for watching. Really appreciate everyone who was in the chat tonight. Even the people that were being feisty in the chat. You know what? My main goal with this channel is I want you to know that God loves you. And so God loves you. And I hope that you were able to get something out of this. And have a good night, everyone.